Alright, we're going to continue with Chapter 5 by looking at Section 5.2. Our goals for this section are going to be to use the ideal gas law, which you learned in a chemistry class. We're going to apply it to pure ideal gases, and we're going to begin talking about what we need to do for ideal gas mixtures. We're also going to very significantly talk about standard states, the STP, or standard temperature and pressure. And when you have values given at STP, you need to learn to think of that as being a molar flow. It's not a volume that they're going to give you. It looks like a volume. It's very deceptive. So this is very important, that when you see STP, think molar flow. And then finally, we're going to start talking about those ideal gas mixtures, and we want to relate partial pressure to mole fractions in a gas. Now, we'll be using this in future lectures, but in this lecture, we're just going to introduce the concept. We will also, in future lectures, start talking about when the ideal gas law is actually an appropriate choice. We know there's no such thing as an ideal gas, but we still use this law. So the ideal gas law. You all know it as Pivnert. PV equals nRT, right? You've seen this a long time. This is the first of the equations of state that we'll be learning. An equation of state, or an EOS, is simply an equation that relates pressure, volume, and temperature of a substance. So PV equals nRT is the most common way that we've seen it, but a lot of times we want to have things on a per mole basis, so volume per mole. We also call that molar volume or specific volume. And if I take this and divide this expression by n, I end up with P little v equals RT, where little v is that specific volume or molar volume, and it's just simply the total volume divided by the number of moles. Now keep in mind, whenever you use the ideal gas law, you have to use temperatures and pressures that are absolute. So the absolute temperature, well, I need to decide if I'm using degrees, well, the SI system or the American engineering system. And SI, I'm going to use kelvins. I'll take my temperature in Celsius and add 273.15. If I'm working in American engineering, I'm going to take my temperature in degrees F and add 459.67. Pressures also have to be in an absolute value. So to do that, I'm going to take the gauge reading and add atmospheric pressure to that. Now, many of our problems will be solved at atmospheric pressure, and so usually we say that the pressure is 1 atmosphere, meaning atmospheric pressure. That is inherently an absolute pressure. If they say that the pressure is a gauge pressure, then atmospheric pressure would be a pressure of 0 gauge. So, the standard state, STP. In this textbook, we're going to use an ideal gas at 0 degrees C and 1 atmosphere as the standard. Now remember, 0 degrees C is 32 degrees Fahrenheit. And so the standard temperatures are 273 Kelvin and standard pressures are all 1 atmosphere. Now if I use the ideal gas law to solve for the molar volume or specific volume in liters and moles, I find that 22.415 liters per mole is the specific volume for an ideal gas at the standard state. If I convert this over to cubic meters relating them to kilomoles, I have 0.022415, and cubic feet to pound moles is 359.05 cubic feet per pound mole. Now to use this, I'm going to take the PV PV equals NT at the actual state and divide by the standard state to get a relationship. So this has an implied parenthesis around these denominators. I want to warn you, gas flow rates are most commonly in industry given as SCFH or SCMH. The SC stands for standard cubic, and then feet or meters, and then the H is per hour. So SCFH is standard cubic feet per hour, SCMH is standard cubic meters per hour. Now, the problem here is that it looks like you've been given a volume flow rate, but this is at the standard state. It's not an actual volume that you could measure because it's really a molar flow rate. So we want to use this STP definition like a conversion factor almost. So let's look at that. If I have 40,000 standard cubic feet per hour of a gas at 183 Fahrenheit and 1.1 atmosphere, let me find the molar flow rate and the volumetric flow rate of that gas. So, to find the molar flow rate is actually really simple. All I'm going to do is use that STP information like a conversion factor. So 1 pound mole is 359.05 standard cubic feet. So therefore, this is 111.4 pound moles per hour. This is a simple calculation because that standard state information is most closely related to moles. To convert to what the actual volume is, I have to do a lot more work. I'm going to take that standard volume, then I'm going to use the ideal gas law ratios to say, okay, well, the actual temperature divided by the standard temperature and the standard pressure divided by the actual pressure. And it turns out that I have 47,500 cubic feet per hour. So we can see that the relationship between these two is kind of minimal. But this is a very simple relationship here. So whenever you see standard state volumes, remember that really that's giving you mole information. Now one last topic for today, the ideal gas mixtures. We are going to frequently talk about mixtures of gases. In fact, we've already done this. Air, we consider air to be an ideal gas. It's a mixture of oxygen and nitrogen. Whenever we're dealing with ideal gases, I've already told you that we never use mass fractions, we use mole fractions talking about these. Well, we're now going to add another way that people talk about this, and it's the partial pressure. So, capital P is the pressure, a lowercase p with the subscript for whichever component is, so oxygen, nitrogen, whatever. That would be the partial pressure, okay? We also can have a partial volume. Now the partial pressure is the portion of the pressure that is due to substance A. And a partial volume is the portion of the volume that is due to substance A. Okay? So another way of saying that would be that the partial pressure of A is the pressure that would be exerted if I had N sub A number of moles of A occupying that total volume at that temperature. And similarly, the partial volume, V sub A, is the volume that N sub A moles of A would take up if it were at a total pressure of P. Now, very significantly, if you have a mixture of ideal gases that are behaved well enough to be called ideal gases individually and together collectively called an ideal gas mixture, again, we'll come back to that in a little while, I can say that the ideal gas law applies to the whole, PV equals nRT, and to the part, the partial pressure of A times the volume equals the number of moles of A times RT. And so what this ends up with, if you divide it through by the total number of moles, is that the partial pressure of A is Y sub A, the mole fraction, times the total pressure. Now this is going to be a very important relationship. So I can relate partial pressure to mole fraction. They're going to be, all tied up together. And I can take partial pressures and add them up, and that will give me the total pressure. Again, it's because these are mole fractions, and I know the sum of the mole fractions has to equal 1. They were all multiplied by P, so the sum of the partial pressures has to equal the total pressure. Now we'll be using this, and we'll be using the standard state information a lot as we move forward into solving problems using ideal gases.